Okay, we're going to look at some other equilibria reactions. There's quite a variety of these, but we're going to keep it fairly simple and look at ionic compounds dissolving in water, whether or not we might get a precipitate or change their solubility, or just in fact ask the question of how soluble they really are. So what are we going to do? We're going to look at solubility. What dissolves? We're going to look at our KSPs. KSP is a solubility product, which is simply another equilibrium constant. And we're not going to do complex equilibria. So when we say something is insoluble, and back in the previous chapters, we said that sodium chloride was insoluble. Well, the reality is virtually nothing is insoluble. Most things are in fact slightly soluble or sparingly soluble, meaning when you put it in water, it's going to dissolve and produce just a few ions. And when we say just a few, we mean very, very, very few, but enough that we can do some math on them. So soluble. So soluble would be back to what we did from the solubility rules, and we know that compounds, for example, of group 1, like sodium chloride, are soluble, meaning that we're not going to find them in this chapter. This stuff really does dissolve and make Na plus Cl minus. Now, we said things were insoluble. Now, very few things are 100% insoluble. Most, in fact, are slightly or sparingly insoluble, meaning that if we took our silver chloride, and when we do these, we're always going to start out with the ionic compound as a solid. It will in fact dissolve just a little bit into Ag plus Cl minus. And with like any other equilibrium problem that we have done, we know the K value for this is going to depend on the temperature, and we're going to have to look it up in a table. So to do these, our equilibrium constant is called a solubility product, and it's labeled as KSP. And again, anytime we see a K, we know that this is going to be the ratio of products over reactants. Now we've gotten away from the fact that we might have exponents in these guys in the last couple of chapters, but now we're back to exponents. So if we, for example, had something like silver chloride, well, AgCl, and we're always going to start out with the solid salt or ionic compound dissolving into its aqueous ions. And we have to remember what their ions are, which is a little more complicated with the polyatomics. But if we have silver chloride, it's going to dissolve into silver, aqueous, plus chloride, aqueous, and the KSP for this is going to equal the concentration of silver multiplied by the concentration of chloride. They're 1 to 1. This is a pure solid, so we're going to leave it off. Now, what if we instead we had iron chloride? Well, iron chloride is going to dissolve into iron and 2 chlorides, and so our KSP is going to equal concentration of the iron times the concentration of the chloride squared. All right, so let's consider aluminum hydroxide. Now again, we are always going to start out with the solid on the left side, looking at how it dissolves, its solubility. Aluminum hydroxide is going to break into aluminum plus 3 hydroxides. The constant for the equilibrium, the solubility product, which is again our equilibrium constant, is going to be our products, aluminum 3 plus, multiplied by hydroxide. I know we haven't done this in a while, but we need that 3 up there for the cubed. And our KSP here is going to equal 2 times 10 to the minus 32. You'll be given these on the exam, and you can look them up in the back of your textbook on any of the homework problems. So we can take and realize there's a direct relationship between the solubility and the KSP. So if we consider, for example, copper chloride and copper bromide, we notice here that K is going down, that this K is bigger than this K. So as K, our KSP, our equilibrium product, again, ratio of products over reactants, goes down, the substance becomes less soluble. So if we want to directly compare copper chloride and copper bromide, the copper bromide is more insoluble. Lead sulfide, for example, is significantly less soluble than any of those, with a K of 10 to the minus 29. So what about the math? Well, the other term that we have is molar solubility. That is how much of something will dissolve. That is going to be the X out of the ice chart. So anytime you are asked for molar solubility, you're solving for X in your ice chart. So let's do one. Silver iodide has a molar solubility of 9.2 times 10 to the minus 9 molar. What is KSP? So we know that we have silver iodide, AgI, is a solid. It's going to break apart into silver iodide. And we know that our KSP here is equal to the concentration of silver multiplied by the concentration of the iodide. So we're going to have an ice because we have two arrows. This is a pure solid, so we're going to ignore it. This is going to start out at 0, and this is going to go up by x, and x, and x, and x. Well, what is x? Our molar solubility, so anytime we see molar solubility, it is going to be, by definition, equal to x, which tells us here that KSP is going to equal, well, if we plug these in, that's going to equal x squared. So our KSP is going to be 9.2 times 10 to the minus 9 quantity squared. And when we take and we square that, that is going to give us a value of the KSP of 8.5 times 10 to the minus 17. All right, molar solubility is the X off your chart. So if we're given instead a KSP and we want to find molar solubility, this tells us that we're given the equilibrium constant and we want to solve for X. Well, what are we going to do? Well, the same thing we've always done. We're going to take our reaction, magnesium fluoride. We're going to start out with it as a solid. We're going to break it apart into its pieces, magnesium plus 2 fluorides. We're going to need an ice. We never need an initial concentration of this because it's a solid. It doesn't matter how much we have. And these guys are 0. Now, this is no longer 1-to-1, so this is going to go up by x and 2x. So we have x and 2x. We know our equilibrium constant, which is a value of 5.2 times 10 minus 11, is going to equal concentration of magnesium times the concentration of fluoride squared, which is going to equal x times 2x squared, which is going to equal 4x cubed. So if we realize that 5.2 times 10 to the minus 11 is equal to 4x cubed, honestly, the hardest part on this is finding the cube root on your calculator. But once you do, you're going to get x, which is molar solubility, is equal to 2.00024 molar. Remember, if you're looking for a molar solubility, it's going to be molarity. If you're looking for a KSP, it will be unitless and an equilibrium constant. All right, we are trying to get the solubility product equilibrium constant, which tells us KSP, for lead chromate if its solubility is 4.3 times 10 to the minus 5 grams per liter. We're going to go, okay, this isn't molar solubility, this is solubility. And this is not what it should be because it should be moles per liter. This is in grams per liter. So we're going to have to do a bit of math. First of all, we know that lead chromate is a solid and it's going to dissociate into lead and chromate. And if we start out with 0 here, we do our ice chart and it's going to go, or ignore that, excuse me, plus x, x, and x. We know that KSP is going to equal x squared. But we've got to get x. And x is molar solubility, and this one is grams per liter. So it means that we're going to have to take and go from 4.3 times 10 to the minus 5 grams per liter into moles per liter, which means that we are going to need the molar mass. All right, so let's get ourselves a molar mass. Well, if we look at the molar mass of the lead chromate, we're going to realize that the molar mass has a value of 323 grams per mole. So if we're going to take 4.3 times 10 to the minus 5 grams per liter, Realize that we've got 1 mole for every 323 grams. We're going to get a concentration of 1.33 times 10 to the minus 7 moles per liter. Well, this value right here is equal to x. Well, KSP is x squared, so KSP is equal to the 1.33 times 10 minus 7 moles per liter squared, or a value of 7.7 times 10 to the minus 14. So if you're given grams per liter, which sometimes we do, you're going to have to use the molar mass to convert into moles per liter, and realize when you have moles per liter, that is your molar solubility, and that is X. We use solids or ionic compounds for some interesting things, including, in this case, a nice visual of some intestines using barium sulfate. It coats the intestinal tract. This stuff is pretty insoluble. So we can take and make things even less soluble. What do I mean by that? Well, we can use the common ion effect. And if we take, for example, lead chloride, we look at its solubility. If we just start out with lead chloride, it's going to have a certain molar solubility. But if we take and we add chloride, we add one of these products to it, we know that our reaction is going to shift back to the left and our molar solubility will decrease. So let's do some math. By the way, wastewater treatment does interesting things like remove contaminants as a function of its solubility. So let's do the molar solubility of calcium carbonate. Well, KSP is given as 3.36 times 10 to the minus 9. When we know molar solubility, we know that's X. We're given KSP, so we're going to write our reaction. CaCO3 as a solid goes into calcium plus carbonate. And we have an ice. We're going to ignore the reactants. We're going to start with 0 because we aren't given any compelling reason not to, plus X and X and X and X. We know that X here, or 3.36 times 10 to the minus 9, is going to equal the concentration of calcium times the concentration of carbonate, which is equal to X times X. And when we finish this, we're going to solve for X, which is our molar solubility, and that is going to equal 5.8 times 10 to the minus 5 molar. That is how soluble calcium carbonate is on its own, just in pure water. Now the question is, what would happen if we added one of our ions, some calcium or some carbonate? So let's look at the molar solubility of calcium carbonate now in a solution of sodium carbonate. Well, what's not changing? We're looking at calcium carbonate. So we're taking CaCO3 as a solid. It's going to dissociate into calcium and our carbonate. We know that our KSP is still going to equal 3.36 times 10 to the minus 9, and that's going to equal the concentration of calcium times carbonate. Okay, why is this different? Well, this is different because we are starting with one of our products. Now, the product that we are starting with is sodium carbonate. Now, sodium, you say, isn't in there. That's correct. The sodium portion is just kind of a medium that we are using to get it there. We have to have that ion as well. So if we have 0.1 molar of sodium carbonate, it is going to dissociate into sodium and carbonate, and we're going to have 0.1 molar here. So do not put sodium in there. It's still inert. We're just messing with our solubility of calcium carbonate. We're using the sodium carbonate to add one of our two ions that are part of the equilibrium constant. This is 0. This is going to be plus X. So we have X and 0.1 plus X. So we're going to have 3.36 times 10 to the minus 9 is equal to X times 0.1 plus X. And you go, oh, great, I can do the quadratic. Or not. You could just let this X equal 0. Why? Because K is small. And so if that X is 0 and K is small, and you solve for X now, X is equal to 3.36 times 10 to the minus 8 molar, which makes perfectly good sense because we added a product and our solubility went down. So the last thing we're going to consider in this chapter is precipitation. Precipitation is going to occur when the concentrations of ions in our solution exceed or are greater than the solubility of the ionic compound. Well, how are we going to do this? We're going to go straight how we've always been doing it. We're going to calculate a Q. We're going to calculate a Q from the initial concentrations and compare it to what the KSP is. If they're equal, the solution is saturated. If the Q is less than, there isn't enough products for a precipitate for insolubility, and therefore there's no precipitation. But if Q is greater than KSP, we have too many ions, it's above what is saturation, and the salt will precipitate. Now, there's some weird supersaturated solutions, but we're going to ignore those. So if we take sodium dichromate and we add it to silver nitrate, we can take and get a precipitate. Now, in order to do this, we have to have enough of both the silver and the chromate ions for this to come out of solution. If a precipitate occurs, that means inherently that our Q, our original concentration, is greater than how much we have to have in order for this thing to become insoluble. So the best way to do this, again, is to just do this. If we have barium chloride and we are mixing it with sodium sulfate, will barium sulfate precipitate out? Well, we go, oh, well, this is chlorides and sodiums and all sorts of stuff. Yes, but if we're going to be precipitating out, we've got to look at our reaction. Our reaction is barium sulfate as a solid. It's going to go into barium plus sulfate. Remember, what doesn't change is that we are always going to have the solid on the left breaking into its ions, and our KSP for this is going to be equal to the concentration of barium multiplied by the concentration of the sulfate. So if we get a mixture where these ions, or the concentration of these ions, are greater than K, we will have a precipitate, which means we need to calculate Q. Q always has the same form, which is going to equal the concentration of barium multiplied by the concentration of sulfate, but instead of being at equilibrium, these are initial. Now, there's one more step in this because we have a dilution. So if we want to know the concentration of barium, it is going to equal the volume of barium, 0.100 liters, multiplied by the concentration of barium, 0.020 molar. Because we're doing a dilution, remember that V1 M1 equal to V2 M2. We're going to divide this by our total volume. Well, our total volume at the end is 150 mils, 4.150 liters, and that is going to give us a concentration of 0.0133 molar for the barium. Now, let's do the sulfate. Concentration of our sulfate is going to equal the volume, 0.050 liters, multiplied by the molarity, which is 0.03, divided by the total volume, 0.150 liters, and this is going to equal 0.0100 molar. So we now have an initial concentration of barium and an initial concentration of sulfate, so we can calculate a Q. The initial concentration of barium is equal to 0.0133. The initial concentration of sulfate is equal to 0.010. Our Q is the product, and that's going to equal 1.33 times 10 to the minus 4. Now, we've got KSP. If we compare Q and KSP, Q is much bigger than KSP, which means in this calculation or in this experiment, we have more of these ions than are soluble at equilibrium. So because Q is greater than KSP, we will get a precipitate. So a precipitate will form.